Clojure, obviously Rich Hickey gave the keynote this morning. Hopefully that intrigued you to maybe understand the kinds of things that he's built and look at those sorts of things. I have been doing software development since I was a kid, and professionally for 15, 17, something like that years now. I did a little bit of C++ work and then spent a long time in Java. Did all sorts of things in Java. Especially I did a lot of query optimization and data integration work. And about 3.5 years ago, I had the opportunity to work on a new system and had a lot of say in what the language is going to be. And I'd been reading about Clojure and Scala and some of the other languages that were coming out in the JVM. And so I had a small team, and we tried out a few of them, and we ended up deciding to go with Clojure. And that team is still using Clojure today. We have maybe 60, 80,000 lines of Clojure. So we've got a large body of, so I've written a lot of Clojure over the last few years, in summary. And before that, I wrote a lot of Java. So I have a lot of experience in both of those. And I'm mostly going to be talking from that point of view, so I'm going to talk about Java off and on a bit. You can replace that with whatever your object-oriented experience is. I think it's probably pretty comparable to the level that I'm talking about. So the 5 areas that I want to talk about today, I want to talk about the difference between values and objects. And this is going to be just a short little intro here. And then in terms of Clojure, parts of Clojure that I'm going to talk about today, I'm going to talk about the collections. I'm going to talk about sequences. I'm going to talk about generic data interfaces. And I'm going to talk about identity and state. There are another 5, 10 major areas that I'm not going to talk about. So you're not going to know everything there is to know about Clojure by the end of this talk. But hopefully these are some of the areas that I have found have really made a difference to me. And I think will help you get a feel for why I think Clojure is a really great language to program in. So I'm going to start by talking about values and what is a value. These are some pieces of definitions I've pulled off of various dictionary sites and things like that. But I think they each kind of get to a little bit of what I think is important. This notion of precision, like I mean some specific thing. When I talk about a value, a particular thing, and that thing has some intrinsic value, some semantic value that I want to communicate to somebody else. And we can agree, we can indisputably agree on what those things are. So if we have something like 20, like you know what 20 is, I know what 20 is. There's different ways to represent 20, 2's complement or this or that. There's lots of different ways to represent it. But it has a precise meaning, and it's semantically evident what we mean by that. So floating point numbers, booleans, A as a character, even strings. Strings are not necessarily immutable in every language, but in most languages people are using today, they are immutable. So I'm going to take those as another kind of value for the purposes of this talk. And all of these things are immutable. That's sort of another fundamental aspect of this. That we're going to come back to many times. Because they have this semantically evident meaning, it also means that they are, we can compare them for equality. Like we know what these things mean, we can compare 2 of them. If we're in the same representation, they probably have the same bits underlying them. That's not a requirement, but I think that's one way to think about it, what a value is. So what about composite values? We really want, this is a standard composite design pattern, right? We really want values that compose. We want to start from these primitive values and have some way to create a composite that contains primitives or other composites, some way that we can create bigger data structures that have those same properties. So I think naturally a question you might ask is, are objects composite values? William Cook wrote up something last year. He's a professor, I think, and he was trying to pull together a lot of definitions of OO and sort of build a modern definition of OO. And he wrote this is a very lengthy thing, which I have completely just extracted a few sentences that I wanted to talk about. And I'm not doing it justice at all. There's a lot of really interesting, useful stuff in the description. So it's worth going and reading the whole thing and forming your own judgment about. But this first line is sort of the beginning of the definition, is that it's a first-class, dynamically dispatched behavior. And I'm not going to talk about the behavior aspect at all. I'm really interested in the data aspect. And he says this first-class notion is really that objects can be passed around just like primitive values. So you can pass them into methods, you can get them as return values, and that sort of thing. And that there's this sort of objects can be substituted for value. And I'm going to fundamentally disagree with this. So it is partially true. Like, it is a composite. It collects fields together so you are creating a composite. But I'm going to contend that it's not a value in the way that we want to talk about values. Objects are typically mutable. And that's like one of the most fundamental ways where we sort of diverge at that point. They're also, if you look at like comparison for equality, like how many, if you've written OO code, you've written equals methods, right? With a composite value, you should not have to write an equals method. It should be semantically evident whether two things are equal or not. So that's another, it's just sort of indicator. And we're going to come back to some of the problems with this at the end when we talk about identity and state. And I'm not going to talk about it too much right now. These are some other signs that mutable objects may not really be what you want for composite values. That this notion of equality, or the notion that to see the state of an object, that you have to defensively copy it out. And you see that at the end, you see that when you need to, if anybody's worked with caching systems where you needed to defensively clone an object before you put it into a cache so that it didn't get messed up by somebody else pulling it out of the cache later. Or if you're enqueuing objects and you need to make sure that that's an immutable copy or something like that of the original object. Or if you've had trouble writing serialization code or composing thread-safe objects. Like, all of these are hard because of mutability. I'm going to contend that mutable objects are not composite values. I'm happy to argue about that later. If you want to see a much longer treatment of this, Rich's talk, The Value of Values, which is out on infoq, is a great but hour-long defense of this argument. So I'm not going to go further. And I'm going to say that what I just talked about, this notion of moving from mutable objects to immutable composite values, is the most fundamental thing that changed the way I think about programming. And it really did. I really had gotten to a point with Java where I'd done everything there was to do with Java pretty much, and at one point or another, and really could not stand to write another iterator loop or another object class, and was thinking about just doing something totally different because I was just tired of it. I was tired of dealing with all the problems that come out from mutable state. And I really thank Rich for for showing up at the right time for me personally, because that really, I say this seriously, it will change the way you think about programming to start from immutability like this. You'll design and write code differently. The roadmap. So we're on to collections. So before we get into collections, just a real brief thing. So it looked like most people there's a lot of familiarity with Clojure already. But it's a list by elect on the JVM. There's also a Clojure script, which compiles to JavaScript, and there's Clojure CLR. It's dynamically typed. It's compiled. There is no interpreter. Even if you're typing in a REPL, each expression you type is compiled into a class and dynamically loaded into the class loader. So you're always in compiled mode. And it embraces functional programming, but also does not rely strictly on functional programming. I'd say it's not a pure functional programming language like Haskell or something like that. It embraces, I think, very pragmatic concerns of things we need to do to write programs to do things we need them to do. So some of the primitives out there, this is how they look in Clojure. So all this is valid Clojure code. Most of these probably are things you would expect to see. You'll notice it's nil instead of null, which is what you'd see in Java. You might notice the 22/7 is a literal rational, so it's a fraction. Those are supported in the language. I don't see them used very often, but it's nice to have them there in the cases where you do need them. The /a is a character, a single character, so instead of a tick something, it's a /a, and then strings at the end. So this is not all of the primitives, but that's ones you might be interested in. So Clojure collections. There's literally 4 major Clojure collections that are provided for you. There are also queues, which I'm not going to talk about, and which aren't used that commonly. And there are also sorted versions of the maps and sets, but they really still conform to the same interfaces and look pretty much the same as these. So vectors are kind of like Aurelius in Java. They're expandable, indexed collections. So, and vectors are what you use constantly in Clojure. You see them all over the place. As you add items, they add to the end of the vector. I guess is all I want to say about that. Lists are sort of the classic Lisp data structure. So it's a linked list type, that sort of structure that you're expecting. New items get added to the front because you just add a new value on the front and then point to the old list. So these are used for Clojure code as just lists. That's all it is. And they're used for other things too, but that's where you see them most frequently. Maps are a series of, it's a dictionary or hash table. It's sets of key value pairs. I've separated the two here with a comma. Commas are white space in Clojure. So I put it there for clarity in this case, but it's totally optional. The keys here, you'll notice, are these colon prefixed things. Those are keywords. So keywords are always basically evaluated to themselves, and they have sort of the similarity to things like intern strings in Java. So they are very fast for comparison and idiomatically used as keys in maps in particular, and also for other things like constants, enumerated values, and things like that. And we'll see them lots in this talk anytime we're using maps. So here, first name and last name really represent like fields in a map. And then sets, of course, are just elements that are distinct, non-overlapping elements, and they don't have any order semantics to it. It's an unordered set. And maps similarly don't have any particular order necessarily. So all of these are immutable composite values. These are not objects. These are real composite values. You can nest them arbitrarily. Any of in the map, the keys or the values could be vectors or lists or sets or maps or other primitives. That's all fine. Equality is based on a combination of the equality partition and the contents of the collection. So you're not defining equality or anything like that. Vectors and lists are in sort of a sequential partition. There's really 3 partitions: sequential, map, and set. And vectors and lists and some other stuff fall into that sort of sequential partition. And you're just going to look at the elements each in turn, and then you're going to recursively sort of compare those for equality all down the line. And then maps, you're just comparing key value. All the 2 maps are the same if they have the same keys with the same values. And that's, again, a recursive thing that happens. And sets, I think, should be obvious. So that's all good. So I would say Clojure collections are real composite values, and they really have this substitution quality that you can replace them for values and functions, and they are better that way. The other sort of aspect of it is you can sort of perceive them as a whole. So you can, because it's immutable, you can look at different subcomponents, nested things, all that, and you're never going to get messed up by somebody else that's changing the thing underneath you, because that's not possible. There are lots of collection functions out there. They're sort of part of the core library. All of these have the ability to count them. Conj is short for conjoin, and that's the way that you sort of add an element to a collection in the natural way for that collection. So vectors add to the end, lists add to the beginning, sets add into the set, maps add a new key value pair. Seek will return a sequence, which is what we'll next major topic we're going to talk about. Into allows you to pour one collection into another and retain that collection type. Empty gives you back an empty form of the collection you have. And I'm not going to go through all these, but like lists allows you to get the first and the rest. Both vector and list allow you to walk in and get a particular nth value in the middle of it. List is going to perform a sequential search through that to get there. Vector is indexed, so it's actually going to be able to go directly to the right index. You can pull out subvectors, replace things. Maps really deal with assoc and dissoc here, or associate and dissociate are ways that you add new key value pairs into it. And you can do things like merge maps and check for containment, get submaps with select keys, things like that. Sets work the way you expect them to, and the disj is a hard thing to say, but that's short for disjoin, which is kind of the opposite of conjoin, which is a way to remove elements from the set. And then there's a bunch of relational algebra set functions that you can use as well, which are useful if you're using sets. I'm going to real quickly here go to, just do a little bit of demo to get the little bit of that feel in there. I'm running Lighttable here, which is a new IDE for Clojure and also JavaScript, and I think very soon Python. It was a Kickstarter project last year. It's not ready for production use, I would say, but I've been experimenting with it just because I thought it was it's got some nice properties in terms of live evaluation. So here it's actually like evaluating things, and let's see. So if we create a new vector, let's see if I can get that to evaluate. There we go. So I just created that v there is a var, which we'll talk about a little bit later, but it's basically a place for us to store things, right? So it's not a value, it's a var, which associates a name, binds a name to a value. So I can take that and I can conjoin that v, I can add a new element to it, right? So you see the 4 was added on the end there, and I've still got a vector. That's great. I can actually go back and look at v, and you'll notice the v is unchanged, right? So these are immutable data structures. So if I wanted to do something with this vector that has the new 4 on the end, I need to capture that and do something with that. It's a new value. So v is one value. The conj, this value right here is another value, which if I want to do something with, I can. So this is the difference between working with mutable data structures and immutable data structures. And that's where it comes up, really. I know that when I first went into it, that it seemed weird for about a day, and then I stopped thinking about it, and it was really not a big deal. So I don't know about other people, but for me, it didn't take long to get used to it. So here I've got a map, which I've put in the Apple var. It's got a name key with a value and a kinds key, and you'll see I dropped a vector inside there, so we're sort of composing that together. We can do some, add some new thing. Oops, it's really hard to type this way. So, and you can see that now there's a new key value pair out there, and you can do more than one of these at a time. That's fine. You can do that too. And just like before, you'll see that the original one is not changed. I haven't modified the original data structure at all. There's a way to sort of get all of the keys out if I want, or I can get all the values out. And then one of the things you do a lot, of course, is retrieving things. So if I want to get out the name, I pass the get, looks up something in an associative collection. You give it a key, and it looks up, it returns to you the value. All right. So something that may not be immediately obvious is that if you have a map, an associative collection, it is a function from its keys to its values mathematically. So that means that we can actually invoke the collection as a function and pass it a key, and it returns to you the value. You see that sometimes. It's useful for containment and things like that at times. Another thing that may be even less obvious is that the keyword actually also implements the function interface, and it basically, when you give it an associative collection, it looks itself up as a key, so it just passes itself in. So this does the same thing. And this is, I've found that this is something that looks strange to people sometimes when they first encounter it. It's done, it's very, very common in Clojure code. So it's maybe the most common way to get things out of a map. Is you're basically using this keyword, a key in the map, as a predicate. And we'll see this come up a couple more times later on. And then another thing you're commonly going to do is check containment. So, oops. So just, does it have a name or not? Oop. So, and then, it's got some else. No, it doesn't. All right. So, all right. Quick demo, just to get a little feel for it. So one question you might be asking, isn't this all horribly inefficient, right? Because we're just taking a value and then we make a new value and we make a new value and we're just throwing values away. And that's a good question. So vectors and maps, which are really the data structures used most frequently in Clojure, and sets also are sort of backed by this tree, and the internal nodes have very wide branching factor, 32 wide branching factor. So the tree is at most like 6 levels deep or something like that. So it's a very wide, shallow tree. And when you need to modify that, say we need to add some new element that goes at the end here to this vector, you sort of copy the path back up to the root, and he points back to all the old structure that's already there. So this old one here is all immutable. It's all still there. And the new one is, on the right side, is a new thing, and it's just got pointers into the old stuff. So it's also got its own consistent set of things. As things sort of go away, eventually they will be garbage collected. You tend to create, so you're basically creating lots of little immutable objects. I don't know if anybody saw Charlie Hunt's talk yesterday, but that's exactly what the JVM works well with. So this is nowhere near as inefficient as you might think it is. It is slower than mutable objects for some things. There's actually the ability in Clojure to take a persistent one of these data structures, make it mutable in a very narrow sort of scope, add a bunch of stuff to it, and then turn it back to being an immutable data structure. And that's a common trick that's used in performance-sensitive code. And the immutable aspect of it never leaks out. You're only doing it in a very limited scope. And if you try to do bad things with it, it will blow up on you. So it doesn't let you sort of it doesn't let you do bad things when it's in that sort of mutable mode. So that's a pragmatic thing, and I've certainly used this in I've written some serialization code and things like that we're basically pulling a bunch of stuff off the wire and pouring it into collections and things like that. And this is using that mutable trick in that case is a huge, lets you get close to Java level sort of performance. So it's important in those cases. All right, so that's collections. So sequences. So I talked about immutable collections as being immutable values, that being like a key thing for me. I think the second thing is really sequences. So sequences are really immutable views into a collection. So it's not a stateful cursor, it's an immutable view. It's basically logically a list, and you can get back from it so the interface that you have for this abstraction is really, give me the first item in this logical list and give me the rest of the list. So you're going to traverse it in order and go through it. There's another function called seek that returns, basically, you can give it a collection. It returns to you a thing that implements this sort of sequence interface. And it also hopefully it will never return you an empty sort of thing, an empty list looking kind of thing. You'll either get back something or nil. and nil is also treated as false. So the seek is often used as like a termination condition check, that sort of thing. Because you only need to access one item at a time, it's very easy to create infinite seeks, and that's fine. You can create something that will generate new values as you use it, or will traverse through an object that is being realized as you walk through it. They are often lazy as you use them, but you can mostly consider that an implementation detail and ignore it. There are definitely cases where you can't ignore that, but a lot of the time you can just forget that's true. So really, this is, if you look at Lisp, it's got this rich history of sort of functional programming based on the list data structure. And so what sequences do is say, oh, well, all that stuff is really based on this abstraction of a list. And so let's lift that abstraction off of the list data structure and just do our functional programming on top of this abstraction. And that allows us to then make lots of data structures work in terms of that same abstraction. Then we open up that library to many different kinds of data structures and things. So what are some things that can produce a sequence? All those Clojure collections we had qualify. Strings can be treated as sequences of characters. Arrays are a sequence of values. File seek gives you back a sequence of files in a directory. Line seek is lines in a file. Tags in an XML doc. Rows in a result set. Regular expression matches. Java iterators, enumerate. There's lots of stuff, right? And you can make your own. So there's tools to make your own lazy seeks or eager seeks or whatever you need, right? So there's lots of things that produce seeks. That's one big thing. And what can you do with them? This is a partial list of the things that are in the Clojure core library for functions to help you do interesting and useful things on sequences. So like, remove duplicates, filtering, mapping a function over them, reducing them down into a function, splitting them or partitioning or grouping them in different ways. There's just all sorts of stuff out there. And usually the first 6 months of being a Clojure programmer consists of writing these functions and then discovering that they already exist in much better form. So every Clojure programmer I know has been through that period. And I'm still finding things like, oh yeah, I never knew that was there. And then there's other libraries, there are other libraries as well. This is the core library. There's other whole libraries other people have written or that are provided as libs to do things with. So sort of the grand abstraction here is to take all that stuff, which is so we basically we can talk about all of our data in terms of this sequence abstraction. And we can take this whole library that we have of functions, which is our code for manipulating data, and then sequence goes right in the middle. So it's the thing that connects it. So you get all of your data, all of the stuff, and you get this whole library of code, and this is an incredible amount of reuse. This is the reuse you were promised by OOO, but did not get, right? Is because you can, all of this data, like how to do these things. You know how to filter or map or remove duplicates. Like I know what those are. I do it all the time, on a vector, but I can go over and look at the lines in a file and I can use the exact same functions and they work the exact same way. So you get like a tremendous amount of reuse out of these libraries. And if you write your own functions, you can use those too. So I have my own functions that do things like walk through a map and apply a function to all the keys or apply a function to all the values or something like that. That's fine. That works on anything, any mappy type of thing that I can give it. So this is huge. I mean, it's a game changer in terms of like how you write your code. And the amount of sort of reuse you get as you go walk into a new set of code and understand what's there and how the data works. I've also found that a lot of like refactoring of code is really sort of trying to step back and think about the data that exists there and how can I make that naturally a sequence of values. And oftentimes, if you're fighting with these functions, like sometimes you'll find like you're just fighting these functions, and there's a reason for that because you're fighting the functions. That's exactly what you're doing, and it's because you haven't really thought about your data in terms of a sequence of values. And usually, if you can recharacterize what you're doing in that way, and it's surprising how often you can, then all of a sudden you can these things start to apply better. And a lot of these that are higher order functions, like filter that takes a predicate or map that takes a transformation function, that sort of thing. Those higher order functions, like what you'll find is that when those functions you're passing in are things that already exist or that naturally are easy to write, like when those start to become easier, you're going in the right direction. So you're not creating anonymous functions and doing a lot of munging around. So one kind of example here that I wanted to walk through, the top function here, line count, just takes a file. And there's a function called reader that basically takes a lot of different things, actually, and courses them into Java I/O reader. And then lineseek is one of those functions we just talked about that produces a sequence of lines out of a reader. So this gives me back a sequence of lines, and then I can just call count, right? Count's what I use on vectors or whatever, but I can call that to actually implement a word count function over. So that's everything you need right there in that top function to count the number of lines in a file. The second one here is a predicate, a file to check whether a particular file object, in this case I'm expecting a Java I/O file object to come in, and you're seeing some Java interop here. So .isFile is calling the Java method isFile on the file object. So if you're interested in how Java interop works, this is the only example of that I think in the talk. So that's how it works, it's nice. So and then file counts here, I'm passing a directory. And I'm going to read this sort of inside out. And when you've been reading Clojure for a long time, you sort of naturally get used to that. But starting down at the bottom, you take this directory, which say it's a string, which is your path to your directory. You're going to create a file as a function that creates a Java I/O file out of it. File seek is going to create a sequence of files, Java I/O files, in a directory. And then I'm going to apply my filter function with this file predicate that I just created and say, just filter out, give me the ones that are files and not directories, basically. And then I'm going to use map. I'm going to map the line count function that I created over that sequence of files, right? And so for each one, it's going to go in and create a reader and count the number of lines or whatever. So I'm going to get back here like a sequence of line counts for each file in the directory. And then I can just use reduce at the end to sum them up. I can take that sequence and crunch them down with plus into a number. It gives me the total line count in the directory. I'm going to take a brief diversion in syntax and say that if you didn't like reading it in that sort of inside-out way, I do like it, actually. So I would probably write the code this way. But there are definitely people that will use some of the arrow macros that can give you sort of an imperative feel to it, a series of steps that you're following. And this really takes that code and sort of turns it inside out. So it starts with the directory. This is the exact same code. It just turns into the file, gets the sequence of files, filters only the files. And then the tricky thing with this arrow macro here is it's going to basically drop the result of the prior function into the last parameter in the next function. So filter file, and then you're going to get the result of the previous step get dropped in at the end. And then the map, the same thing, gets dropped in at the end. And a general convention in the library is that sequence functions take the sequence as the last argument. And so this double arrow here leverages that by, it's usually better for sequence-y type of things. Collection functions, the first set that we saw, things like conj and assoc and dissoc and all those type functions, they take a collection as the first argument. So there's another macro, which is just a single arrow, and that one actually drops the result of the previous one in as the first argument. So that one tends to be better for when you're working directly with a collection. So as you go through the library, you'll find that if you're aware of that distinction, it can help sort of alert you to which sort of mode you're in. This macro is going to rewrite what you have here at compile time into exactly the same code that we just had, or very close to that. That's probably the last time I'll talk about macros too. So it's another whole broad area. So let's see, time check. We're halfway in, right? Okay. So generic data interface. This is where the meat of the talk is, actually. So, and I didn't know exactly what to call this, this section of the talk. But it's something that I really deeply appreciate about Clojure. So I'm going to try to figure out how to talk about it here. But so say you have some domain model. This is a domain model. I run conferences, some conferences. So this is like a domain model for a conference. Probably not a very good one. It doesn't really matter. So we've got a talk and a speaker and things like that, right? So in Java, I actually went over for that speaker thing here. I actually just took the first 3 fields and I went over to Eclipse and I wrote down some fields and then I hit all of the things that generated code after that. So I generated a constructor and I created the getters and setters, I created the hash code, and I created the equals, and I created the toString. So, whoo, I'm there. So, but this is crazy. Do you agree this is crazy? That we have to do this for every single entity? And then usually it's not even what you want, right? You have to go in and change it after that. So I don't know, this has always irked me. So like this notion of having, what you're doing here is you're creating this custom data, we're creating new functions, right? These are this set Twitter, get Twitter, and they're only scoped to this particular object. Like they're only good for this, right? If you actually want to like reuse them in some way, you need to create an interface that has more methods and then extend, put that interface on all the things that need to get that out. And that's crazy. So Clojure does not do that, and that's one of the things I really like about it. And the other point to make here is that going back to the composite value thing, is that you don't need the hash code and equals fall out of the composite value stuff. So you don't have to create those. You're just not going to do that. There are ways to customize printing and do things like that, but usually you don't do that either. But so the important part is those fields up there. That's the essential part of this. There's a ton of ceremony here, right, that we can strip away. So sort of the easiest way to represent an entity, not the only way, is to represent it with a map. So I can just say, I'll just represent me. Here's some keywords that represent my fields. There's my values, and I don't have to say anything else, right? I've got equality, I've got hash code, I've got toString, all those are built in. If I want to actually go get the values out of it, I can use all the things that exist for maps already. They're already there. One thing you might miss is a type of some kind. So one solution to that is to add a field, and that tells you what the type is. This is not sufficient for everything you need to do, and we'll get to that in a second. So here's some more entities, just some examples, an attendee, a sponsor. You'll notice that email is in all of these. There's a common key here. So instead of like, if I wanted to go do an email blast or something, I need to get the emails from all my sponsors and attendees and speakers or whatever. I need to go create an emailable interface, and then I need to have all of those domain entities that implement that just so I can call get email. So I know that just to tell the language that get email on these set of kinds of objects means the same thing. And that's, you don't need to do that in Clojure. You can just use concat to put all those things together, and then you can map the email function. So email here this is where we're using the keyword as a predicate. And you'll see this very commonly. You're just going to map email over the entities, and it's going to give you back a sequence of email addresses for everybody in your organization. And at that point, I have a sequence. So I can do things like remove nil if I want to. I can do distinct, which will remove duplicates from it. I can sort it. There's lots of things I can do with it at that point. As a sequence, I can just start working with it as data. I'm always in this mode of having data that I already know how to work with and functions that I know how to work on that data. So they're sort of like universal getters and setters, like these keywords. You do still have to agree on keywords at that point. If you wanted to, like if I'd called one email and one email address, then I don't get that. So that's still there. You know, you can't do everything with it, but it's not semantically aware, right? So you still do have to exercise care and thought as you program, but that's okay. So if you want to, so you just use it as a map, right? And you can add new fields into it with a source. You can get things out of it. We've already talked about that a little bit. If you really want to, you can grab all the keys that are in your entity. So think about what you'd have to do if you wanted to grab all of the fields that are actually currently set in your Java object. You could do that with reflection. That's ugly code. You don't want to write that code. And you just wouldn't do that. You would never ask that question in Java. And there's lots of cases where it's useful to talk about your objects in that way and to look dynamically at the fields that are in your object and do things. You might also, like, maybe you need to troll through all the values out there and look for, to uppercase all the values in your domain model or something like that. You could easily do that in Clojure. That's not a big deal. But that would be, there's just not even any way you would think about doing that in Java or something. Another thing you get sort of that falls out of all this is this notion of traversable entities. So we've been talking about single entities, but once you get sort of nested things, there's actually a set of functions that are these -in functions, get-in, update-in, assoc-in, that let you actually walk down and talk about things in nested entities. So you can do things like, say I have a track, I really meant a talk there. So if say you have a talk that has a speaker in it, and that speaker has a first name, I can do this to walk down through those nested entities and pull out the first name of the speaker in a track or a topic or whatever. Similarly, and that's cool, but you can kind of do that with chaining methods or whatever in Java and stuff like that. In this respect, nils and does the right thing in most cases for that. Update-in, though, is really cool because I can say traverse through track down to speaker, down to his last name, and apply the uppercase function down at that point. And it'll give you back the new top-level entity that has this deeply nested changes in it, right? And this is really, really useful. Assoc-in is kind of similar, but it's specific to keys. So it lets you add a new key value pair at some nested point down in your data structure, or in more than one nested key value pair. And this really goes to, you can't, at times you'll build these, you'll have these big composite values that represent your domain, like big chunks of your domain. And you can just apply a function to them to move to a new value of the domain. And it's a composite, there's a big composite value on both sides. And I've said something very concise to make that happen. And the way that you get from one to the other goes back to the state model, which we're going to talk about a little bit. It works well along with that. There's a couple different ways that are in the libraries that you get to walk through and do things across the entire data structure. So this is an example of using the Clojure.walk library. And there are some issues with Clojure walk, and there are some reasons not to use it in some cases, but it's really useful as well. It basically will walk through nested composite values and applies this function. So it basically applies this function to every nested node inside this composite value. So this thing is looking for inside this, this big domain structure that I have. Look for something that's associative. It's map-like, and it has a key that is Twitter. And if so, prefix it with the @ symbol. So I decided I'm going to represent things differently in my domain model. I don't want just the ID. I want it to be like @ID, whatever. So this lets me walk through the entire data structure and apply that change. It's doing a depth-first tree walk, so you are going to have nodes on the stack. That's one of the reasons that, so you can't actually blow your stack with large domain models like this. So there are some cases where you need to be careful about how you use this exactly. Zippers is another functional data structure that gives you, it allows you to traverse and modify the tree as its own functional tree-like data structure. And it's beyond the scope of this talk. There's lots of stuff out there written about it. I've written a very lengthy article that's out on DeveloperWorks or something. If you go search, you'll find it. And we've built a bunch of things that allow you to apply tree transformations to trees using zippers, and they can be made very efficient. And so we've gotten a lot of mileage out of that as just a general technique for editing and manipulating trees, which come up a lot. So back to the representation of our entities. Sometimes it's useful, a lot of times it's useful to switch behavior based on type. And you can do that. You can certainly do that with a attribute that's telling you what the type is, and you create a function that looks for that type and that sort of thing. But there is another way to do this in Clojure, and that's to create a record. So def record allows you to create a speaker record that has this set of fields. So if you go back, think back to that big Java Eclipse nonsense, this is saying the same thing. And it's actually literally going to generate a Java class under the hood that has those fields and implements a lot of that stuff. It's probably not exactly what you're imagining as far as the implementation goes, but conceptually that's exactly what it is. And it is idiomatic to capitalize the name because it's really creating a Java type under the hood. And we're going to leverage that to some degree later on. So like if you look at the class as a function that does .getClass on an object. And that's going to tell you that it's a Java speaker class. And then there's some factory functions, some constructor functions that get generated automatically from def record. One of them is this arrow type that lets you sort of positionally take all of the fields to initialize it with. There's also one that lets you pass a map of whatever key value pairs you want. So you pass just partial sets of fields and things like that. Generally, if you've only got like one or two fields, you're probably going to use the positional one. But I find if I want to write code that I expect people to read later on, typically these two lines of code are not together, right? The record is defined in one place and it's used somewhere way different. In that case, I really want to pass in a map that has the explicit fields in it, so people know what I'm talking about. So I probably use the map one more commonly. But and once you get it, a record actually is a map. It implements all the same interfaces as map. It looks like a map. You can associate, get it. Everything that I've talked about up till now in terms of the generic data interfaces is all still true, except for Clojure walk, which I think doesn't support records right now. But almost everything else that we've just talked about still works literally identically. You wouldn't have to make any changes to any of your code. So here's a little example of defining a card in terms of a suit and a value. And I think there are defensively better ways to actually implement this. But as an example, so say we define some suits. So we've got a vector which has all our suits in it. We've got a way here I've done a little bit of Clojure stuff to build up the set of values that I want to use for my the different values in a suit. So range 2 to 11 is going to give me all the numbers from 2 to 10, basically. And I'm going to map string over it. So I'm just going to turn those numbers into strings. And I'm going to concatenate that sequence with this Jack, Queen, King, Ace values. Then I'm going to turn all those into keywords. So there's some little code there to do that. And then so I can create a full deck I'm using a for comprehension actually, which we're not going to talk about much. But for every suit in suits and every value in values, I'm going to invoke the constructor. So this is going to return to me a sequence of card instances with all the possible suit and value combinations. So now I've got a full deck. It turns out that shuffle is actually one of the built-in Clojure core functions, which randomizes a collection. So you can actually shuffle. I didn't have that on here, but you can shuffle your deck if you like. It happens to work really well. If you want to cut the deck, take the top half, put it on the bottom. You can basically drop the first half. That gives you the bottom half. Take the second half. That gives you the top half. You can then concatenate them on top of each other. There's actually a function called split at, this is one of those things where you just troll through the library and you'll eventually find the thing you want to do. So that it says basically split at a particular index. So you can there's an alternate implementation based on that. So just some examples of using sequences and records together, things like that. So polymorphism. So we haven't talked at all about behavior and how we sort of dynamically choose which code to run, because polymorphism is good, right? We want to have the ability to have different kinds of people, but then apply something to all of them, right? This comes up all the time. It's a good thing. We want to do it. You can just do it with conditional logic, right? I mean, you can do that way in imperative code, and you can do it in OO code, and that's, in some cases, that's the right answer. The two major mechanisms for sort of dynamically choosing a function implementation in Clojure are multimethods and protocols. And they're both useful for different things. So I use both on a regular basis. Multimethods are going to switch based on a dispatch function. So they let you do a broad range of things. So they're very flexible, but they're a little slower. So, and then protocols are really switching specifically based on type. So they have a much narrower range of things you can switch on. It happens to be exactly the same thing that you would switch on in OO, and it happens to be very fast in the JVM because that's what virtual function calls are based on, things like that. So it has some performance advantages. It has a little bit less flexibility in those terms. Let me get in a little bit of example here. Talk about it a little bit more. So if we're going to define a multi-method, here I'm defining a function area that by default is going to take a single argument, and I'm going to specify the dispatch, some arbitrary dispatch function. And here, again, I'm using a keyword as a function. So colon type is a predicate that's going to apply itself to an associative value, which is the incoming function value. And then the result of that dispatch function is going to let me choose which of these method implementations I'm going to pick. So based on a value, so colon circle or colon square are the two values that might come out in this case, and they're going to allow me to pick one of these methods. Here in the argument list, I'm actually destructuring the map inside the argument list. So I'm taking in a map and I'm actually assigning the variable radius to the value of the radius key in the map. I haven't talked about destructuring at all. I'm not going to talk about it anymore. It's awesome and it's a good thing, but I'm not going to talk about it anymore. So that, doing the same thing in the square one, when you apply this, so I've got an entity that's got type square, side 5. I can apply area to it. It's going to go through dispatch function, pull out square, look up the square one, and eventually invoke that, right? The side times side, right? So that's great. So one of the reasons this is a little slower is that I ran two functions there, right? I ran the first function, the dispatch function, and I ran another function. So it is a little bit slower, and it has gotten faster over the years as the implementation has been tweaked a little bit. I think there is hope that it could be made faster still with invoke dynamic, and it hasn't really been worked on much yet, but I'm hopeful that will be true. So protocols. So here we're going to define a protocol named shape, and a protocol is actually not just one function; it's actually a collection of functions. And so you will naturally be reminded of, you might naturally think of it as an interface. And I think it's actually a dangerous way to think of it because while it shares many characteristics with interfaces, that's not where I find that it shines in code. That an interface from a Java perspective is really a collection of functions. And in Clojure, I've found that namespaces are really a more natural way to define an API as a collection of functions. That's what that is. The namespace does that. It collects functions that you can use. I found protocols to be excellent for representing SPIs, sort of service provider interfaces. What's the base part underneath that I want to plug in? So I might have this really broad API, and it might surface some parts of the SPI directly, but it might also build a bunch of utility functions that are over the top that are the same regardless of what SPI you're plugging in on the bottom. But anyways, in this case, we're just using it in a very narrow sense here to get polymorphism. So we've created this protocol shape. Again, it's capitalized. It actually does create Java interfaces and things under the hood. And that's how we start to get some performance benefits, is we can leverage all that polymorphic call stuff that's in Java and is really fast. I've defined records for circle and square. I didn't have those in the last slide. But because protocols switch on type, I really need something. I need a type that's specific to my entity. So here I've defined real records with circle and square, and then I extend the protocol shape to the type circle and to the type square. And here I actually implement the function with and the implementation is exactly the same, right? I've extended these both together, but there's no reason that has to be done. You can extend a protocol in one place to one type. You can extend it in another place to another type. You can later on come in with some new code and extend it again at that point. So it's an open system, just like multi-methods are an open system. And then you invoke it exactly the same way. The only difference really is that I'm using the record syntax to construct things there. All right, so identity and state. So we got 10 minutes to talk about identity and state. So there's no way we'll do that, but we'll try. So I'm going to go back to objects for a second and talk about, say you've got a talk named bacon and the abstract is bad. So clearly not a good abstract. And in this case, so for objects, identity is wrapped tightly around the object, right? The object has an identity to it. It has these fields in it. And an object is kind of like a whiteboard, right? You're gonna write some, I wrote these values down on my whiteboard, and then someone comes along and they want to change the abstract to something better. I'm gonna erase abstract and write a new value in there, right? Is good. So good, we made it better. So we might say at that point, we should really make this into a workshop, because we should really focus on this a little bit more, I think. So now we've made a couple changes here, and we've still got, if say you got the original, say we were back here and you got this original version of the object, then like you've got the same object, right? You've still got the same identity, and it's changed underneath you. The thing that you had is now changed, and this is where mutable objects change over time. They exist in a timeline, but they don't have any way to communicate to observers that they're changing, right? You just can go ask it things and you might get different answers, right? It's very unsatisfying. So you look at all the problems with Java concurrent. The last time I was here, I did a whole hour talk about problems with Java concurrency. That's what the talk was about. You go look it up, it's got a whole list of things, right? And I remember Rich was at the same conference talking about, here 3 years ago, talking about Clojure for the first time, I think. And afterwards, he told me how terrified he was by the whole talk. But, but that's why he's working on Clojure, right? So, so the problem is that locks and concurrency models start to address that, but they can't address it. I mean, it's not possible for you to perceive all of these things together at the same time. And that's something that composite values provide. You can actually get a value, it's not going to change. I can do whatever I want to it at that point. I can look at it in whatever way I want. It's never going to change. Nobody else can mess me up. With mutable objects, somebody else can mess you up. I forgot I had this in there. So I've got this slide, this quote from SICP, famous computer science book, scheme, et cetera, et cetera. And I think it's really fascinating because they highlight in here that dealing with objects change in identity are a fundamental consequence of the need to grapple with time in our computational models. So they're on it. They're, as always, this stuff's all been done, right? So Edward Muybridge, I don't know if everybody's ever familiar with this guy. This is back in the 1870s. So Leland Stanford, the governor of California, hired him to settle a conjecture about whether when a horse galloped, whether all 4 feet came off the ground at the same time, right? And nobody knew. They were debated it, right? So what he did was he set up 15 cameras and he put a tripwire to the shutter and stretched it across the race course, and so that as the horse went down, it would trip each of those shutters. And so you got 15 frames. You can clearly see in the second one, he's off the ground, right? So I see some analogies here to what I'm talking about, in that we're sort of perceiving our software and time in our world as continuous. But in our software, we don't want it to be continuous. We want it to be discretized. We want it quantums, where we can perceive the state of a composite value at a particular time and look at all the different parts of it. We don't want to like go say get legs and get the stuff from the first frame, and then get head and get the stuff from the second frame, and get jockey and get the thing from the third frame, or whatever. We want to pull a particular frame out, and that's our composite value. And then we can do whatever we want with it, right? Time's gone on, and we're whatever. And we can choose to perceive this value at different time, but every time we do, we get a whole, complete, perceivable snapshot. And this is the core of the Clojure state model. So this is not collapsed down in one thing. I've lifted the identity off the top of the value. And identity, it still exists. We still have those things where like, we have this talk, it's still the thing that's changing through time, right? I still care about that as a concept. But it's a series of composite immutable values that exist through time. So I've got it here, and then I invoked a function, a pure function that took a composite immutable value and produced a new composite immutable value, and then I invoked another function, and it produced another one. So each of these things inside the identity is an immutable value. It's good. And the state is just, we happen to ask for it now, and that's what we get. That's our state, right? And time might be continuing after that, and that's fine. We've got something, a thing that's good at the time. So representing state, there's really 4 different things we have for representing state in Clojure. Vars we've already talked about a little bit. I'm not going to talk about them much more. Oops. And then atoms are really this notion of I've got a single timeline and I want to coordinate access to it, but I don't need to coordinate with other things. I just got like a counter or a single value that I want to coordinate. And it will go through a series of changes, but it doesn't need to coordinate with something else. Refs are when I really need lots of things that are I need to take a bunch of these single identity timelines, and at times they need to meet. I need to perceive the multiple bank accounts at the same time and apply a transaction that takes me to a new state in my world. And I don't need to involve globally the world to do that. I need to involve the identities that are actually changing or being read at that time so I see a consistent view. Agents are a little like atoms in that they are single timeline coordination, but they're asynchronous. So there's basically a queue in front of it, and you say, I've got some state over here, I'm going to apply a function, but I don't need the result back. Just go apply this function when you get to it, and apply a series of functions in a row. All of these have this property of perception. So all of these have a thing called deref. Well, the atoms, refs, and agents have this thing called deref, which is actually, there's a little bit of syntax sugar with the at symbol. So you can say at an atom or a ref or an agent, and you get back the current value, a current value, right? It's a consistent value at the point where I perceived it. And doing that is cheap. So it's OK to do that all the time. And so as opposed to like actors or something like that, if I want to get a value of an actor, I have to send it a message, right? And it has to send me back a value in some way. But I can always see the state that's out there as an observer. And that's really important. So I talked about atoms. This is an example with a counter. So you declare an atom, and then it's just applying this series of functions in a row, right? And every time I call this ID function, it's going to swap the counter. It's going to apply the inc function, increment, it's a +1 function, to the current state of the atom, and then put that back in the atom. And if 2 threads come in at the same time, try to do it at the same time, that's OK. One will basically spin lock, waiting for that to be OK. So there's limited things this is useful for. But anytime you'd use one of the atomic classes in Java Util Atomic, that's the equivalent kind of thing. And there are some other use cases for it too. So refs are really interesting. There's actually a whole software transactional memory system, which I haven't mentioned yet, so which is kind of a big thing. So this allows you to coordinate multiple identities together. So we can create a ref. Again, it's a thing that wraps around a value. It's all of these wrap around a single immutable value at any given point in time. So this yo-yo function, I'm going to put that thing in the one, and we're just going to swap it back and forth between the 2 refs, right? So I need to coordinate the identities, these 2 different identities that have values. And multiple threads might be banging on this at the same time. That's OK. What you do there is you're going to just set I'm going to read the values. Here I'm dereffing. I'm going to read 2 values at a particular sort of time point that includes my 2 refs, and then I'm going to swap the values of them. That's all. And then I'm going to return it just so I can see it too. And then the key difference here is that there's a transaction. So doSync defines a transaction boundary. And that says to the STM, in this thing, I'm going to go make some changes to some set of objects, R1 and R2. There could be other objects out there too. I don't care, right? I don't care about those. But I need to make sure that R1 and R2 are in a consistent state together. And then I'm going to make a change that takes them to a new state together. So this allows me to get the A, C, and I, out of ACID, are all there. So that's great. It may find out that somebody else is trying to do the same thing, right? So in that case, the transaction will fail and it will get automatically retried. So the STM is protecting you from that. And there are a bunch of, there's another whole talk to talk about this. So I'm not going to try to do that. But it actually uses MVCC under the hood with adaptive history and snapshot isolation and a bunch of stuff. So it's just like Oracle or something like that, some database technology for dealing with multiple things, and it's optimistic. So you're able to, if things go ahead well, then you can do a lot of stuff in parallel. There's a lot of concurrency benefits. I'm almost done, by the way. So agents is basically the same thing as what we had for atoms, but there's a queue on the front. So you're sort of sending functions over to something. And at any time, I can perceive it with deref. So to sum up, my contention is that objects are not composite values, and that programming with composite values is awesome. Way more awesome than objects. Collections in Clojure are immutable composite values. Sequences are an awesome abstraction for sitting between composite values and functional programming. Clojure has a wealth of tools for providing generic data interfaces over all that data stuff that you have. And finally, that identity and state are a distinct thing from values, and Clojure has a bunch of tools for dealing with that as well. So if you're interested in this stuff, 2 talks that are on infoq, Are We There Yet? Is really about the identity state stuff. Value of values is really about why values are important. Those are 2 I'd recommend. That's all I have. Thanks.